Hi, everyone.
Hello.
Great to see you. Hola, compañeros. I got such a long introduction that it's really hard to say anything more than that. I'm Tomasz Stanczak.
And I'm Piotr.
All right, let's start then. Obviously, if you were looking at agenda, maybe many of you were thinking, like, what the hell is Ethereum? Okay, we're coming here for .NET. Why Ethereum? So Ethereum is a different state of mind as well, because you go there and you start from .NET world, you are in enterprise, and you think that your life is set, and then you decide to try something different. Try blockchain, and you go and you see that's all those like hackers, cypherpunk people there, and you try to adapt and change. And what Ethereum is, it's a public blockchain. It's a public blockchain with virtual machine. And it's obviously being blockchain is also peer-to-peer network. Peer-to-peer network with tens of thousands of nodes connecting together and talking and synchronizing the data and doing things, running smart contracts. And it's a blockchain that is kind of like second generation blockchain after Bitcoin that many of you probably have heard of, delivering the consensus algorithms and payment models. Ethereum brings the decentralized, trustless, distributed computation. And when we think about distributed systems the traditional way, it's a bit like, I don't know, SETI program, looking for alien life on different planets. And we say, it's a big task, let's distribute it. Let's split it into smaller tasks, and everyone gets a piece, and we'll be looking for a solution together because it's a big task. And we split it, and it's more efficient because we don't do that much as we would do on one machine. And then you go to the blockchain world, and the blockchain world is like this, like lots of paranoid people that think like, yeah, they're looking for alien life, but if they find it, maybe they won't tell me. Or like, what if they fake that they found the alien life and just not trusting anyone? We're all paranoid. And this is the approach where everyone does everything and verifies themselves, like everyone verifies everyone else. And this obviously opens, for technologies, it opens amazing challenges in learning how to solve those technical problems that arise from the fact that every single node on the network will have to process every single transaction, block, store all the data. And this is a bit of in a blockchain world, an abstraction for these ideas of those places in the world where this trust is really missing, the trust for the governments, corporations, others, and you try to build something that idealistically solves those problems. But still, the technology part is cool, and that's why we started Nethermind, and it's a group of fantastic people that I had pleasure to work with for the last 2 years, delivering a client for the network, for the distributed blockchain network, the protocol implementation that does everything, so the whole network can run only on the application that we've delivered, called Nethermind. And it's written in Dotnet Core, and that's why we are here today. And when we write something in Dotnet Core, then especially if it's open source cryptography, a blockchain style business, these are the questions that you hear, right?
Yeah. Like, does it run on Linux or does it run on OS X? Can you develop in Linux? Well, yes, you can. It runs and it works.
Yeah, and like people, it's always, you go to people and they will be asking, will it run on Linux? Like this .NET, will it run on Linux? So there is some work for us to convince people that yes, with .NET Core, we are Linux native in a way that, yes, we run our instances, our nodes on Linux. I have to keep repeating that. And the second question is, like, why .NET? And why .NET?
It's just getting better and better.
Yeah, and we love .NET. That's the reason. We just love .NET. No, it's really fast, and it's getting better, and that's what we see. So the challenges that we have when thinking of the blockchain, delivery of the blockchain solution. So first of the things like cryptography, most of the libraries, they are in C++, right? Things must be fast, but more likely, like it's just that was the language that most of the cryptographers will start with for the reasons of speed and so on. And then you have to have those libraries accessible via C#. So for most of them, you'll be like just wrapping them and p-invoking the calls. For some other libraries, you'll try to look at what's available in .NET, and will tell you about what libraries are there that you can use and how efficient they are a bit later. Then there is the problem of synchronization of blockchain, which is really connected with the other challenge of P2P that is potentially hard. So you have those 10,000s of nodes, you connect, you assume that they can try to lie to you, that they can try to attack you, send malicious data, and so on, try to invoke denial of service on whatever you do. And you have to collect like gigabytes of data and process them to be able to work with the network. Then something that is very interesting from the point of view of building the database is the reorganization. It's like you build a blockchain, you process things, and then they don't have, in most of the cases, they won't have initially the feeling of finality, I mean like the property of finality, which means you write the data, you do something, and then the data can suddenly go back in time and go other path, which means that you have to build a database and a solution around the database that will enable you to just go back in time. So like to remember past states and be able to continue on top of the past states. And this all of those are very interesting problems, technical problems. And the random access, it's everything in Ethereum that is stored is keyed by hashes. And hashes, these are cryptographic hashes, which means they're totally randomized. So whenever you read something, there's really no logic in the keys that you're retrieving. So most often, you'll be reading totally random from the hard drives. And very often, you'll be writing very often. And there's a bit of like reference to benchmarking.net book. Like you build a benchmark and we just show you one benchmark, the benchmark where it goes well. But it's like the introduction that we did achieve something in at least one of the benchmarks, and what the competition is. Like we entered the market where we had the client written in Rust, a client written in Go called Geth, and the Pantheon being built at the same time. It's a client written in Java, which means that you meant to deliver exactly the same thing because blockchain is meant to repeat the same thing, and everyone verifies if everyone does exactly the same thing. So it's really like a perfect place for people that are crazy about benchmarks and comparing and improving performance, because really you cannot explain that you're doing something very different. You're all supposed to do the same thing. And the results that we've seen were really, really amazing, and the community sees that. And we even see like another type of benchmark that we haven't mentioned today here. It's like a social media benchmark. As you build something, you release a new version, and then for a few days you're waiting for responses from people. And you see it's like execution time. Someone posts, it's 7 hours. Someone sends something like, oh, it's fast. Then someone posts logs, and it's like an outlier, like 21 hours we see there. And I think even with Dotnet Core 3, we've seen that they were posting all these technical benchmarks, like how quickly the things were done, these minor improvements here and there. But then you knew that there was this feeling in Dotnet Core team that they're waiting for the users to actually show what's the real results. So this is always important when you deliver the product to the users to actually start listening to the feedback on how they feel your product is performing. And obviously, we do have a set of micro benchmarks for some critical paths. And those critical paths are usually around the arithmetics on the big integer numbers, the things around serialization that is specific for Ethereum, binary serialization. It's only used there. Also, the things around hashing, our implementation of hashes, and so on. And we have one golden benchmark that we keep running. We've been running for the last 2 years. It's 100,000 blocks loaded from the testnet network. And for most of the project, the sooner you build this kind of like integration benchmark, that you'll be always, like they'll touch many parts of your system and you'll be able to refer to. The easier for you will be to build a full understanding what you are benchmarking as a whole project forever, right? Like later you'll start, like if you try to adapt to your application in a way, then like you'll be benchmarking different thing. We have one that we keep carrying on and looking at the numbers and always allows us to look at everything there. Okay, I had a very short demo time just to show you the project because everything is colorful here, obviously, but the reality is not that colorful, really. Let us run the, like, the blockchain has no magic. It just started, it works, and I just always try to convince people that, like, it's really simpler than people say it is. So this is a project launching and starting synchronizing the blocks. And you see it's displaying there. There's sometimes like 9, 5, 6,000 blocks per second downloaded from the network. Stops, maybe like, okay, 17,000. And it's all about like finding the nodes quickly that you can talk to, agreeing with them, like doing the handshaking, establishing the secret keys for the processing of data, and synchronizing the network, and then processing the blocks, and so on. Let me go back here. So,
yeah, the magic.
All right, I mentioned that there are crypto libraries in .NET world, but obviously you have C or C++ libraries. That's like very natural place to go is very wide, comprehensive crypto library called Bouncy Castle. And it's a port of Java implementation. And it does a lot. Many people will use it for different implementations of the elliptic curves and hashing solutions, encryption schemes, and so on. But it's really very slow. And it's allocating like crazy. And then you have to keep looking for the bits and pieces in different libraries. And this will be very often for you. Like you go for cryptography, you're already told that you shouldn't write cryptography yourself. So you have to look for probably like very small C libraries, and they have to be battle tested. And then you maybe want to try to find something that relies on GMP, the amazing arithmetic library on C that was maintained since like 1991, right? And this is all about using something that's battle tested, and it's probably everybody who's improving performance is improving those libraries. And actually here I'll let Piotr to interrupt me, explain me something about elliptic curves.
Yeah, all right, so probably most of you have heard or actually used the RSA, right? Which is well-established and well-known asymmetric cryptographic algorithm, right? Where you have a private key for creating your digital signatures, and you have a public key for verifying, right, these signatures. So with the blockchain, actually, you don't use the RSA here, you use something else. ECC, or elliptic curve cryptography. Anyone ever heard of that term? Okay. Oh, quite a lot of people. That's really cool. So the basic question is, why would you use something else if there is already an existing solution that does the job? Well, and usually the answer is because it's more efficient. So if you take a look at this comparison chart, you can see that, for example, in order to achieve this 128-bit security, for the RSA, you need over 3,000 bits of the key, and for the elliptic curve cryptography, you need somewhere around 250 bits or a little bit more. So what it does in general, like why is it secure? Because with RSA, we deal with prime numbers and we deal with factorization problems, so it's all mathematics. And the same applies to the elliptic curve. It's also based on the mathematics, right? So let me show a very nice interactive demo. And here is this nice website. So let's say, here's my elliptic curve, and there is the equation for that curve. And I have 2 points here. This is, let's say, point A and a point B. And I want to add these points to them together. So I need to have this line that intersects through both of these points. Here it's, let's say, C prime. And in order to get this addition of these 2 points, I need to multiply its y coordinate by -1. So it's like mirroring over this x-axis, right? So that's the addition of these 2 points on this elliptic curve. And I could also add these points multiple times together. So let's say is my point G, and I can add it to itself like G plus G plus G, and so on, k times. So what does it have to do with the blockchain? If we get back to our slides, what was the magic shortcut for the? Thank you. Okay, so if we get back here, yeah, I always have to click duplicate. Instead of operating on this infinite real numbers field, the blockchain says we will use this set, which actually you can think of standard for efficient cryptography, and we'll use this finite field of very big integers. And why is it actually secure? Because it turns out that I can add I have a predefined set of my starting point called G, which is the generator point with given XY coordinates. I have this field defined, and I can add this point to itself k times, which would be my private key in that scenario. So I can easily compute my public key based on adding this private key many times, but I can't really find out how many times I had to add G to itself to find out what is the key, this key parameter. And it's based on discrete logarithm problem. And this is what it makes secure as RSA, but much efficient in terms of size of our secret key. And yeah, this is why we use this native C implementation, because it was just faster.
Yeah, so like one important thing here is this like addition. When we talk about elliptic curves, like we assume that addition is practically free and multiplication is expensive. So like whatever operations you do, the multiplications are the only things that you look at. And all those multiplications, you can use them like with doubling and squaring, and you introduce those solutions, and they come in those libraries like SECP and so on. But to work with everything in Ethereum, with the integer arithmetics for the curves, for hashing, for a virtual machine that also operates on, everything operates on 256-bit integers. And one important thing is like, when you work with integers or longs, the standard types, you just multiply them without thinking what multiplication is, because, or maybe you do, but you know that you send them to the processor, and processor just has the multiplication of two long numbers, and it just gives you the result. The moment when you work with 256 bits, you can think of applying the like scalar multiplication, but then you always have to have some like software support to get the carry and do the operations properly. Also, Ethereum uses everywhere the Bigendian notation for all the bytes that are sent over the network or even executed in the virtual machine. And obviously, on most of the machines that we use when we deploy .NET, we'll be having the little endian. So at least like x86, AMD64 architectures will be little endian. So it's important to look at the like road of .NET Core in the last 2 years that really matched the needs of this like low-level computation or like modifications working with bytes for the sake of cryptography of Ethereum. And we'll show you a few small examples of the things that make a huge difference. So the one thing is the addition of the binary primitives, the things that allow you to change the endianness or read from big little endian byte streams. All the basic types, the struct types for the value types in .NET. And this will be like, obviously it uses spans, and then it gives you the longs, integers, and so on. And I think we have a benchmark here for these. Like, do you see properly? Let me make it slightly bigger. I'll show you the code first. That's here. for the reverse. So we look at the byte array. Again, here. I want to just invert the array, revert the array. And we think first of some like naive implementation of just like iterating over the array and replacing the bytes, like the last one with the first one and the penultimate one with the second one and so on. And then applying it. And this will be our baseline. Then we think of something like magic, right? Was it magic? Array reverse. Then there is span version since recently, and us bytes as span and then reverse. Then we look at the AVX2 version maybe, because we are in the space, like we assume that this is 32 bytes, 256 bits. So we can use the Dotnet Core free intrinsics, right? So you can use AVX2 version, load the vector, shuffle the vector. The shuffling on the 256 bits is happening actually on two 128 lines, so you cannot really revert everything, but just like two 128 lines twice. And then we have to permute 4 longs together, and we can store it back. Anyway, we have what we need. We reverted the 32 bytes of the array. And then the last thing actually uses this most simple API that you have, which is binary primitives, reverse NDNS on the longs, and we just use the tuple assignments here. And that's it. Like third, zeroth, second with first, we revert them. And we use also memory marshal to cast our bytes to ulongs. And now we go back to those results that maybe you remembered and see that the progress is quite great. And the thing is, things like that, even as they seem micro-optimizing, the moment when you have to execute virtual machine, where those things are happening millions of times, over and over again, just to be able to execute arithmetics on integers, it happened to end up being like a few % of the time of your application when you optimize these. And what's the most pleasant part of it is that this very simple operation of reverse NDNS it's properly efficiently compiled into the swap. And it's the fastest. Like as you see, it's nearly 20 times faster. Let's continue here. Oh, big integer improvements. So I'll go back, like I showed you that we're using 32 bytes arrays. So we really care about 256 bits integers. They're not directly multiplied or added on computers. So we have built-in type in C# in .NET, which is called big integer, which allows you to multiply or add or do whatever with them, the numbers that are of arbitrary length. Right? So it doesn't have to be 32 bytes, can be anything really. And this is great generalization, plus what is very important is like if you move from .NET Framework to .NET Core, you'll probably for free, you'll get like 30, 40% or even more of the improvement when you work with big integers. And in many places, like on the allocation-wise, the time-wise of execution, there's lots of improvements at the beginning of .NET Core, I think here from Axel here, and further, the people that were introducing the algorithms for numerical methods, like there are multiple different algorithms that are improving the integer arithmetics depending on the size of the numbers. Like if you go for numbers beyond 1,000 digits, there are some algorithms that only then kick in and start to be faster when you multiply the numbers. And all of that is coming in .NET Core because the code was open source and someone thought, okay, it's important for me, so they prepared a PR and it improves things a lot. And before we implemented our own int256 type, we're using big integer and just upgrading from 2.0 to 2.1 in .NET Core improves things like 30% of the, not on that place, but like the whole application benchmark that I was talking about, like the one that does a lot of other things. It's a massive improvement. And span of T, obviously, like there's this dramatic change in how we could work with the stack on virtual machine, with the binary serialization, deserialization of all the things that were coming from the network and we're sending to the network. And this is an example of like how we handle stack. Like we do not use stack data structure or any like byte arrays. We just have a contiguous byte array, and we pull those for like multiple levels of execution, and then we just practically just slice it whenever we need to pop something off the stack, and whenever we put it back, we just write to span, and that's it. And we move the head of the stack. And again, to show you some benchmarks. So a few things are hidden here, but generally what we do here, we're adding two numbers. There are 256 bits each, right? 32 bytes each. And here we already use the new constructor from big integer. These 2 Boolean values at the end were not available before. And these 2 Boolean values say is unsigned, is Bigendian. Which means that previously you had to do that outside of the constructor of big integer, and you had to like try to optimize this reverse endianness to handle the signed byte yourself and so on. So this is no longer the case, and that was this like 20–30% improvement that I was talking about in 2.1. Now we're adding the bytes here and write them back to the stack in our case, but it's just a byte array. Then we have something that we've implemented, but not fully. Like, so for some operations, we've implemented this type for 256 bits integers operation. So it's just a struct with ulongs. This is actually 512 for multiplication. But if we go, also like to say that we've implemented it, it will be a bit too much because it's based on the library built by Rick Slatky, and it's called diriclet.net. And we just, it was only supporting up to 128 bits, and we've added some operations for 256 bits. But the whole thing is, this is a struct. It uses ulongs for very efficient operations on adding and so on. And it requires this reverse endianness here, just to load the things. But the important thing is, because it's not generic as big integer is for multiplications and additions and so on, when you look at the benchmarks, it allows us to avoid this thing. Like while adding 2 zeros, this is a scenario when we're adding 2 zeros, it seems very similar. For adding 2 big numbers that are actually causing the, forgot the word, like the overlap. Overflow, obviously. When you have an overflow, then actually we see big integer allocating. Because for the bigger the numbers, the big integer class starts to create some kind of like calculators, the temporary values that it stores just to support its generic calculations on big numbers. And the last thing, small thing to look at is also the fact that by just adding refs here, like by adding not with the overload operator, but actually refing the integers, we got additional 20% improvement on this addition. All right, I think actually we need to speed up. The one last benchmark, let's not switch it, but you can see here we have the array reversal. Oh no, okay, this one we discussed really. Great. Great. This is what I was mentioning, that you have some algorithms for improved multiplication. This is one particularly well-known algorithm in cryptography. It's called Karatsuba multiplication method. And it just uses the fact that you treat addition as something for free and multiplication as something expensive. What it does, more or less, it replaces the multiplication of 2 big numbers and a standard approach which would allow us to use 4 multiplications of smaller numbers. It replaces it with 3 multiplications and around 3 additions in a smart way. It's explained here, but maybe you reach later for these slides or look it up. And it's just because you assume that addition is practically for free, and you want to just remove that multiplication and improve significantly the multiplications on very big numbers. Okay, let's talk a bit about hashing functions. And Piotr will have soon some nice example with Blake. Yeah?
You have to click again.
Okay. Yeah. So because it's so important in cryptography, and I really want to show you something that you can use in many cases, like these are hashing functions. And very often you'll think like this is a bit of magic, and like maybe you will use something and not the others. This is just one of the benchmarks, but if you go to that link, there'll be lots of different cases, like on Windows, on Mac OS, and on consoles like Xbox and so on. And one important thing for you is like if you ever decided to use MD5, and it actually takes a lot of your processing power for storing some data and hashing it, just switch to one of the ones that you see here closer to the top. XXHash, CD64, FARM64. You may have some massive improvement, and there are some examples online when people were replacing that in the projects from MD5 to one of those more modern hashes and got some immense improvements. And this is for non-cryptographic hashes. And there's a big difference. Like for non-cryptographic hashes, you don't expect that you'll never find any collisions. For cryptographic hashes, you will maybe lose some performance, but you will target the cases where you have never any collisions. The moment you find collisions, so two pre-images that give you the same hash, you consider the cryptographic hash to be broken. For non-cryptographic hash, you also want to learn about like the simplest one that you can implement, that probably you were using it for get hash code in C#, the FNV1 hash. It's considered to be super simple and actually the fastest for the smaller byte arrays, like maybe like 8 to 12 bytes. That's why we use it very often for our structs. But everywhere else you probably want to look at XXHash and CTHash64. Okay, these are cryptographic hashes. And Ethereum uses SHA-32256, but it's actually like a slightly modified version that was before that. It's called catchak. And nowadays, the more and more popular hash, the hash that becomes more and more popular is Blake 2B. And it's very fast, and it also has some nice flexibility for lots of cases, like different lengths of the digest, and the rounds that you can execute the compression function on, and so on. Again, like MD5, apart from the fact that it's slower, it's also as broken, right? So like use Blake or use SHA-2 or 3 for any case when you need speed. But use Blake when you need security, but use Blake when you need speed on top of it.
Okay, so let me show the sample of our Blake 2 implementation. Actually, we didn't have to implement it fully, only a part of it called compression function. So here is the code. Let me close it. Blake 2. So that was our first approach to the Blake. And it was just a port of the already existing library in Java. Okay, and usually, just if you take a look at the crypto code and the name of the variables, you can tell that it's secure by nature, right? But that's just how the crypto code usually looks like. So this is the first version of our implementation, where you can see we've been doing array copy, some rotation, so a lot of operations on bits, computing in for-each loops, then some additional allocations, and so on. So this was like the first version. Then we, of course, run some profilers, run micro benchmarking, and we came up with the optimized version of a Blake. So here it is, the improved one. And there isn't that big difference in the code, actually, but we are, of course, using these binary primitives here. And for example, here we are operating on spans directly. We are also using this Moore-Marshall casting, so we can cast directly these types on the spans. And that's pretty much it. It's just .NET Core improvements. So let's maybe take a look. What are the benchmarks?
Don't forget about stack alloc there, right? Like it always makes it look so much more pro.
True. And these are the improvements. So there was the first version. This is the optimized version. So it's almost 20 times faster. And as you can see, the allocation over 20 times less allocation, or almost 30 times less. And we can go further with this. There is an existing code using FOX and SIMD intrinsics. I'm not sure if it's open. Yeah, it's open here. So we can go even further with utilizing the new runtime intrinsics namespace.
This is actually a good example of the new cryptography libraries appearing. People start to play with intrinsics. And we have a library for Blake2B that just appeared recently. Someone wrote it with AVX. We've actually staggered approach like SSE, AVX, depending on which one is available on the machine with the processor. And we can use it now. And we hope that there'll be more and more of that appearing and making our life easier. Great. Let's say sometimes you want to have the hashes very slow, actually, for password protection. Just because of time running out, I'll tell you quickly that just remember those names for hashing the passwords with Salt. You want to use Script, or even the newer one, the Argon 2, that is based on Blake2B. The whole idea of hashing the passwords is that you want to make it slow, so people cannot brute force all the potential combinations because it would take them ages, because the hash is slower. And specifically for Script, because it uses the key derivation function that allows you to parameterize it, you can make it even slower by just changing the parameters of how many times you hash the same thing. So any other solution for hashing, especially if you want to use performant hashes for passwords hashing, this is the wrong way to go. You want to make it slow. We have a part here about not allocating the byte arrays with .NET. Actually, we use .NET for all the networking. This is a port of the Java library, NET, for all the TCP and UDP requirements for us, sockets, and so on. And it provides a solution with the byte arenas that it allocates per threads, 2 arenas per threads. And if we launch the memory profiler, we see that when we launch the application, we have something like 300 megabytes allocated just for the 16 megs each byte arrays. And then it allows us to rent and return buffers from that arena as chunks of that byte array. And the buffers have a lot of methods that allow to combine them, like split the body and header and maybe just keep replacing headers. In our case, we just use it for some framing, the encryption, and the message authentication codes that we add, and so on. But the whole thing is, interestingly, it practically uses the pooling through reference counting on the objects. So the objects that you rent and return, they have the ref count, and you have to manage it yourself. Like when you release the object, you have to call release. When you borrow the object, you have to increase it, and you say, OK, so I'm using it now. And then you can enable some models where you actually can track if you have some leaks. If the object is finalized, it will actually throw an exception if the ref count was not 0, which means someone pretends, claims that they're using it, but they don't have any reference anymore, so we finalize it through the garbage collector. So have a look at NET, have a look at how byte buffers are built there. It allowed us to build this zero allocating network stack that's a pipeline of 5 or 6 processors that do the framing, the encryption, and addition of MAC, and also the compression with Snappy compression library. OK, we have time to talk about 2 very interesting things. Something that is from blockchain world and is very popular in blockchain world, but these are data structures that you can use in some other projects and are particularly targeting some scenarios around data, huge data sets. And this particular one, Bloom filter, it's used, for example, in Cassandra. It's used in RocksDB database that we use just to increase the efficiency of searches. And also here below, you have example of, I think, Akamai CDN network, content delivery network. They wanted to make sure that they do not cache immediately the data requests that are issued for the first time. They said that something like 70% of the traffic, or maybe I'm wrong, maybe 30% of traffic was the one-off searches, and then they didn't have to serve it for a very long time. And I wanted to avoid caching it immediately, only cache it for the second time. But then you would have to build some massive indexing of checking what was called once and what wasn't called. So instead, what you can use is a Bloom filter. And that link will lead you to some very simple explanation where you can click and experiment with it and understand it very quickly because it's a super simple concept. What you do, you take the data that you want to store and you hash it and you extract something like three bits from that hash. And because it's a proper hash randomizing thing, so it really doesn't matter. You pick 3 bits and you set them on like a byte array. In our case, the Bloom filter is just 2000 bits, right? 2048 bits. And you set those, and for every single data that you write, you set 3 bits. And then when you execute a search, you can just check if what you're searching for, if you extract these 3 bits of data in the same hashing function, if any of those bits is not set, then for sure the data is not there. And that's why it's probabilistic, because if the 3 bits are set, they might have been set by other data. But if they are not, for sure you don't have your data there. And for example, RocksDB, when it saves data to the file system, it creates the blocks. And when you're saving the keys, it just composes the blocks of data of something like 200 megs of data, for example, and it stores the blocks. And then for every block, it keeps the Bloom filter that allows you to check very quickly if the data most likely is not there. But if it's a positive, it might be false positive. And you can analyze the percentage of chance of like what the false positive would be. And here's an example of like how good results like MI had when they switched it on, switched it off to check the results. And the one last thing that's super important for blockchains, and you can also use it for many other projects, it's a hash tree. It's something that you're probably very familiar with from Git in a way that you are using it, but maybe not necessarily know that how exactly it works. So Merkle trees are a super powerful concept when all the data that you have in the tree, however big the tree is, you hash it, and then for every single node of the tree, you just hash the concatenation of hashes of the children, which means that you go all the way up, and you have just, in our case, it's a 32 bytes hash at the very top, which is a root of data. And that root of data, which is 32 bytes only, contains the information about every single bit of data in the entire tree. Like you change a single bit of data, if your hashing function is properly random, is a random oracle, then you change the state root as well. And nobody can find a collision because your hash is strong, right? And this is used for like verifying very quickly and efficiently the data correctness. So in Ethereum, the full data tree, a single state is 40 gigabytes of data, but it's just 32 bytes that you need to verify that someone else has exactly the same state. And this is extremely efficient. It's stored in the block headers, and it's used by all the blockchains, but as you see also in other solutions, maybe IPFS being a bit blockchainy, but Cassandra definitely not. Riak, also key value store, Tor, Bitcoin. And Ethereum uses Radix Tree, which means that there are some spatial optimizations for like when you traverse the tree, instead of using just the Merkle tree the way it is, you traverse it and you build the address of the account very quickly. And the Radix tree allows you to actually combine some of the paths and include them on the edges of the graph instead of the nodes. So as you see here, this is 4 letters in the one path. You don't create four nodes. And then what Ethereum really uses, it's like modified Merkle, Patricia tree, or trie. And I think we won't have time to go too much into details here. But generally, it's combining all of those concepts of the Merkle tree, of the spatial efficiency of the Radix trees, and a lot of hashing that leads to this 40 gigabytes of state. And it's around 300 million nodes nowadays. And what we have to do is, just to give you the example of what we do on the networking layer, we pick the root, and from that root, we have to find all 300 million states by just starting from the root and sending requests to, for example, 100 different peers that are connecting. And you have to assume that they may lie to you, so you have to verify the hashes all the time. They may have various latencies, either not respond or respond with delay. They might be disconnecting, connecting back. And probably what's even more important is that every 15 seconds, the blockchain probably rehashes around a few thousand, 20,000, maybe a few 100,000 of those nodes. So you want to start with the root, but you don't want to save what you start with. But you want to save the leaves first and then go back. Because the leaves, they change the least, and the root changes all the time. We reached the question stage, but I don't think we have time for questions. Do we?
Yeah, unfortunately, we don't have time for questions right now, but during the break, everybody that wants to ask a question can ask you, guys.
Thank you.
Thank you very much. Tomasz Stanczak and Piotr Gankiewicz.